We're gonna get started. I think everyone who's going to be here is hopefully here, and everyone grab some food. Um, Today is our November meeting, and then I do not have a speaker lined up for next month yet, so if anyone wants to speak, otherwise I'll start hunting down someone probably starting next week. So if you want to volunteer, now's the time. One quick announcement before we get into our presenter today. I just want to give an update about the Julie Lefevre Endowment. So all the finances from the core workshop that was done in September are almost settled. So we'll be writing a check for about $4,500 that will go from the core workshop to us, and then that'll go to the endowment. And then we're still waiting on the AAPG check. So once those are both in, it'll be probably close to $16,000. I think that will be in there. So, and then we just have to fundraise the last what, like 8,000, 7,000. So yeah. So and then it'll be at the 25,000 mark, and then it's self-sufficient after that, but we can keep adding to it. Yeah. So that's just a quick update on the endowment. That's about it. So I'll start by today's presenter today is Bob Shaver. Bob Shaver received his BSc degree in geology from Wayne State University, Detroit, Michigan in 1969. After serving 2 years in the U.S. Army with overseas service in Thailand, he returned to Wayne State University and obtained an MSc degree in geology, emphasis on hydrogeology, in 1975. In October 1975, he began employment with the Water Appropriations Division of the North Dakota State Water Commission as a hydrologist. Primary duties included exploration, development, and management of the state's groundwater resources. From December 1980 to May 1981, he took a leave without pay from the State Water Commission to act as a consulting hydrogeologist with Tetra Tech International in the Sultanate of Oman. Primary duties involve determining the occurrence, movement, and quality of groundwater for coastal villages in the Musandam Peninsula. In May 1981, he resumed employment as a hydrologist with the North Dakota State Water Commission until his retirement in April 2013. His talk today is titled Qualitative Assessment of Groundwater Recharge in Glacial Fluvial Aquifers in North Dakota Using Stable Isotope Analysis. So everyone give Bob Shaver a hand.
How much Doc Milton to give me a leave of absence?
Oh, that was well, I think that was it was really the state engineer that allowed that. That was at a time when state employees weren't getting much in the way of raises. And so we were thinking maybe we should go to work somewhere else. And so they decided, well, we'll I had a chance to go do this. And so actually through Roger, you're the one that at Johnson UOP there, that there was it's word of mouth kind of a thing. But anyway, yeah, it was really a nice little interlude, to go over to the Middle East there and work in a really different environment. So it was kind of fun putting this together. This, as Ben said, I've been retired for about 10 years, but when you I was looking at this slide when I was going over this talk, and it's really nice being retired, that I don't have to go out in conditions like that anymore on a drill rig and put in monitoring wells or sample, so it's nice to leave it up to the younger staff to go out and do things like that anymore. So now I'm not really familiar with fiddling with laptops here, so just give me I've just got to
use these arrows to go back.
Gotcha. All right. We got her? All righty. So stable isotope, environmental isotopes of O18 and deuterium are ideal groundwater flow system tracers because they're both constituents of water and they're conservative. These isotopes have been used in groundwater investigations to evaluate recharge areas, elevation of recharge, groundwater surface water relationships, leakage between aquifers, aquifer recharge, and mechanisms of salinization. In modern groundwaters, the H2, H1 ratio, O18, O16 ratios reflect average values of precip in our recharge zones. And we dealt a lot with buried valley aquifers in North Dakota. They're important sources of groundwater, not only in North Dakota, but North America, Europe. And in North Dakota, buried valley aquifers consist mainly of sand and gravel deposits overlain by glacial drift, which is comprised predominantly of till and underlain by bedrock shales, sandstones, and siltstones. And so these deposits that kind of encase these buried valley systems are not very transmissive. And so we don't feel in many of the areas that you get much in the way of groundwater recharge. And we see that because of multiple advances and retreats of continental glaciation environments, they've created complex stratigraphic sequences characterized in some areas by fluvial inhomogeneities that we refer to as short circuits, that short circuit that overlying glacial till, and they facilitate groundwater recharge to underlying buried valley aquifers. The fluvial short circuits generally are small scale features that are difficult commonly to detect by test drilling or geophysical methods. Some areas of buried valley aquifers are characterized by low dissolved solids concentrations, calcium, magnesium, bicarb type waters, and major ion chemistries that are similar to meteoric waters in shallow, unconfined aquifers, suggesting the occurrence of overlying fluvial short circuits. Well, meteoric water, and we're going to be using that term eventually here in this presentation. Meteoric water is defined as water that's been recently involved in atmospheric circulation. Based solely on major ion chemistries, it is inconclusive as to whether some of these deeper groundwaters and buried valley aquifers represent good recharge areas facilitated by these fluvial short circuits, or areas where older Pleistocene water may be trapped. Stable isotope signatures of O18 and deuterium, therefore, can be useful in differentiating these relative groundwater ages. So what we did was collect 19 precipitation samples, both rain and snow, for O18 and deuterium from the Oaks area, the Oaks Aquifer in southeastern North Dakota, to develop a local meteoric water line. And I'll be showing you a schematic of that in just a bit. Samples also were collected from 5 ponds that had developed just as we were seeing spring snowmelt, but before the frost zone in that shallow aquifer dissipated. So we get a lot of ponding that occurs from that redistribution of snowmelt, but it doesn't infiltrate right away into the aquifer. And then we also collected 32 groundwater samples from the Oaks Aquifer for O18 and deuterium and compared those with the precip samples that we developed our meteoric water line. The Oaks Aquifer was selected because we knew a lot about that system, and we know it's a shallow, superficial, unconfined aquifer, so it should be characterized by meteoric water, modern water. Groundwater samples then were also collected for this study for O18 and deuterium from a leaky and a non-leaky area of the Spiritwood Buried Valley Aquifer in western Sargent County, just a little bit east of the Oaks Aquifer area. And we also collected samples over the years from the West Fargo Buried Tunnel Valley Aquifer system in eastern North Dakota. And these isotope analyses were compared with the Oaks area precipitation and Oaks Aquifer isotope analyses to provide a qualitative assessment of age and recharge. And this is just looking at your most common O16 species, atomic weight 16, 8 neutrons, your O18, 10 neutrons in the nucleus, a heavier, but you'll notice the percentage is very small in relation to your most common O16. The same with the H1, 1 neutron in the nucleus, deuterium, the H2, again, a very small percentage, but they're natural occurring again and stable. That's the key. And for expressing stable isotope ratio variations, the absolute abundance of isotopes is not usually measured in natural waters. You're only measuring the relative difference in the ratio of the heavy isotope to the more abundant light isotope of the sample with respect to the reference, and that's what we make the determination on. The reference is your Vienna standard mean oceanic water. That's SMO. And the relative difference is designated by the Greek letter delta, and by definition is delta equals that ratio of the sample minus the ratio of the reference divided by the ratio of the reference times 1,000. And the R's are those ratios, O18 to O16, deuterium to H1. Positive values indicate sample enrichment with regard to V small, your reference, and negative values indicate depletion with regard to V small. And that's what we're going to be dealing with here in our areas of the hydrologic cycle, is the depletion. Based on the differences between the samples and the reference, because those differences are small, we multiply that difference, that ratio, the comparison of the ratios, by 1,000. So this is kind of the key then at looking at how these isotopes fractionate throughout the hydrologic cycle. Stable isotope fractionation is due to slight variations in the physical and chemical properties and is proportional to the differences in masses. And the vapor pressures of the different isotopic molecules of water are inversely proportional to their masses. So therefore, the lighter species, H1O16, has a significantly higher vapor pressure than the H2O18. As a result, water vapor formed by evaporation of liquid water is enriched in the lighter component, while the remaining water is enriched in the heavier isotope. When water evaporates from the surface of the ocean, the vapor that's evaporating is enriched in your lighter species because the H1O16 has a higher vapor pressure than the heavy, and as a result, the O18 and deuterium values of water vapor in the atmosphere above the ocean are negative. The depletion of heavy isotopes in precipitation relative to the ocean water is the result of removal of moisture from the atmosphere by condensation affected by cooling. Therefore, there's a real close relationship between isotopic concentrations and temperature. And this is a good schematic diagram showing this. To the left, you can see our V-smol reference 00. As we evaporate, more of the heavy isotopes are left behind. So our initial moisture, water vapor, is depleted. We have the minus values in O18 deuterium. As we move inland, get our first rainfall events, the heaviers preferentially will fall out, leaving the water vapor in our precipitation then becoming more and more depleted. As we move into the continent, higher elevation, cooler environment, more and more depletion takes place. And you can kind of see this in a contour diagram of O18 and deuterium, looking at the Rocky Mountain areas here to the left, to the west. You can see the more depleted values of O18 and deuterium with this altitude effect, much cooler precipitation. When we look at our interior plains area, moving up through the Midwest towards North Dakota, you can see a more gentler decline or depletion in O18 deuterium as our temperatures decrease. We call the latitude or altitude effect. And this is just a schematic diagram now showing what I referred to earlier as what we call a meteoric water line. And one would expect that, again, based on the physics and chemistry of these isotopes, that our cooler winter precip, particularly our snow, should fall down in the more depleted areas of our deuterium, H2, and O18, and that as we get warmer summer precipitation, we should see less depletion in our O18 and deuterium. And so you do see these dashed lines here kind of showing that above the meteoric water line, if your vapor source is more arid, you'll tend to get values that fall a little bit above. If you get a little bit more humid, a little bit below, so you do get scatter across there, the meteoric water line. You'll also get a flatter slope if you're looking at evaporative loss from like a river, reservoir, or lake, but we're going to be dealing strictly with groundwater and just our precip. So North Dakota, one of the reasons why any given day, any given week, any given month, we can be affected by a different air mass. And the red area kind of shows roughly North Dakota's position, and you can have a Gulf air mass affecting your precip. You can have a Pacific air mass, a little drier, a more temperate, a very cold Hudson Arctic airstream air mass, cold, dry. And that gives the volatility here that we really see in North Dakota. One of the things that we didn't do in this study is to try to take each precip event and see which air mass was the predominant source of that precip event, because you'll get a little bit different adjustments or values, but in your O18 deuterium analysis. But that wasn't the purpose of this investigation. But it does give you a little noise. So this is a map showing the Spiritwood Aquifer. I've kind of shown it with dark arrows here, kind of north-south trending in eastern North Dakota, a major buried valley complex that extends up into Canada, down into South Dakota, Iowa, a major glacial drainage area. And first, we're just going to take a look at the Oaks Aquifer here down in southeastern North Dakota, Dickey County towards the South Dakota border, and then move over a little bit to the east to the Spiritwood Aquifer in that area, and then up to the West Fargo Buried Tunnel Valley Aquifer system in Cass County. So this is kind of a schematic diagram of the Oaks Aquifer. It's what we kind of refer to kind of up-down system. It's a lake plain, delta, lacustrine, and an outwash channel environment, and it's truncated to the west by the James River Valley floodplain deposits that are predominantly silt and clay. So you don't have hardly any flow from the aquifer to the Jim River. So you've got a kind of a hummocky topography it's a lake plain, fairly flat, maybe roughly on average 10 feet of relief per mile. So you wind up with a lot of little depressions, small depressions. Those represent kind of net discharge areas. So you get a lot of your rainfall, snowmelt redistribution. It's kind of what we refer to as depression-focused recharge. And then during the summer months, discharges by evapotranspiration. So very little underflow, say, to a regional stream or another aquifer system. Again, kind of an up-down system. And this is just a plan view. The James River here shown to the west in the vicinity of Oaks, a little thicker, coarser deltaic deposits that grade down into that glacial lake Dakota lacustrine deposits, and they get thinner and finer grained till we get down to the South Dakota border. To the east, you've got these outwash channel deposits, probably emanating from the Oaks moraine along the eastern margin of the aquifer. And this is a cross section, that north-south section. To the left there, the thicker sand and gravel delta near the city of Oaks, grading down to silty, sandy units as we approach South Dakota. This is the transverse section at the bottom, and that little bottom O represents that outwash channel that's overlain sometimes with some silty, sandy deposits, a little bit of clay mixed in, possibly lacustrine in origin, and then sand of the Oaks aquifer. And again, this just shows that up-down system that I talked about, local recharge, discharge areas in the aquifer. It's all drainage, is basically all internal. So here are the 19 precip samples that we collected over a year, both snow and rain, and you can see the nice distribution to the south, the left bottom, the much more depleted snowfall samples, and then a fairly large break, and then our rainfall examples, much less depleted, and a little bit of scatter across, and that's the regression line that we calculated for that distribution. But the main thing is you kind of see there's a really a distinct spread between your rain and snowfall events. We compared that then with the weighted mean global meteoric water line of Yurtsever and Gat. Did I do that?
I think.
You can just get
it's in your figure.
Okay.
So now this will show up.
All right. Good. See, I'm not advanced with the high tech here. I still have a desktop. So anyway, so it compared very nicely with our meteoric water line, global meteoric water line of Yurtsever and Gat. So then we go to those pond samples that we collected just post snowmelt, but before infiltration, and those are the areas shown here in green. And you would expect that's from snowmelt, recent snowmelt. They should have a much colder signature, which in fact they do. But it's interesting, instead of most of, we used to feel that you'd get most of your recharge, almost all from depression-focused spring snowmelt events, that they're the key events that recharge our aquifers. That because we generally have a moisture deficit throughout the growing season, a lot of that rainfall doesn't make it down to recharge. It's lost to evapotranspiration. But this kind of showed us that, we've got a good mix, that we're not only getting a fair amount of water from our rainfall events, but we're getting a good chunk of recharge as we expected from the snowfall, but even during some of the growing seasons. And after working down in the Oaks Aquifer for a lot of years, I was down there when in, say, June or July, you'd get what was almost like a monsoon, where we had to quit working and wait for things to dry out for a day or two. So there's summer precip events can be very significant. So let's move over now then to the Spiritwood Aquifer here, just east of the Oaks Aquifer. And we're going to look at a section, and this is a schematic diagram, really just a really rough schematic, showing the Spiritwood Aquifer here in yellow, to the west overlain by a till sequence, excuse me, and then we get some kind of lacustrine, silty, sandy, silty clay deposits in the overlying drift, and then further west or east, a section where the till is now overlying the Spiritwood Aquifer. And you can see here that we have little local discharge areas here to the topographic low areas, Mazzaro Slough and Dill Slough. The Inglevale Aquifer intersects the Spiritwood in this area. Basically, we're looking at our Spiritwood Aquifer as like a buried line sink. Water moving downward to the aquifer, upward from the bedrock units, and then down gradient laterally. And so we're going to look at a piezometer nest that we installed right around in this area here with some sand, superficial sand dunes. We put a group of nested piezometers. This is just a schematized, like trying to just show a possible fluvial short circuit. And we put a group of nested piezometers in this area, and that's what we're going to look at right now. First, other than collecting just at that piezometer nest, in that what we felt was a leaky area, we collected samples from the Spiritwood Aquifer, and they're shown in red here. And you see they fall right in with meteoric water signature of the Oaks Aquifer. So we're looking at a modern recharge. We're facilitating recharge to the Spiritwood Aquifer in that area. And so if we look at the piezometer nest in that area, up at in these little black areas shown here, that's our screened interval of all the wells in the nests. And we have this superficial kind of dune sand, and then these lacustrine, silty clay silt, sometimes sandy, excuse me, and then some overlying sand, possibly from the remnants of the Ingle Vale, but most likely at the top of the Spiritwood, and then definitely deeper sand and gravel deposits of the Spiritwood, and then our bedrock. And you can see that the 018 deuterium is not very depleted as compared to the other samples that we looked at for cooler snow samples. So it further suggests that we're moving a fair amount of recharge downward to that deeper buried Spiritwood system. Well, then if we move over to a piezometer nest here, where we're outside of the lacustrine, silty, sandy, kind of leaky area, and we're in just straight till, and kind of remember that till, third, silt, sand, clay. So the hydraulic conductivity is very small. We don't expect a lot of movement of water through that till down to the Spiritwood. But if we look at that nest there that was installed, here you see the weathered clay up top, the screened interval here, and then the screened interval deeper into the till, 80 or so feet, a little over 100, and then down to the Spiritwood sand and gravel. The shallow clay has a less depleted signature, which you'd expect. Infiltration's getting down, even though it's low hydraulic conductivity. You do get fractures and other secondary porosity permeability that's going to move water downward. But as you start to get into your deeper unweathered till, you can see here we get very depleted values. But when we get to the Spiritwood, we're up here again at much less depleted values. So what's going on? Well, the Spiritwood at this site, we're down gradient. So we would expect movement of that water in the leaky area still influencing the flow regime further down gradient. So if we didn't have that upward drilling to show that fluvial or that lacustrine, silty, sandy recharge area, when you'd see something like this, that's kind of a signal, better go chase up gradient there and see what's going on. Even though you got straight till here, you know, you can see that you're not moving much water through that glacial till. So then the last section then is going over to the West Fargo Aquifer, and that's a series of tunnel valley units. Dave Ripley did the work on that in the 90s and kind of determined a variety of, or a number of relatively discrete tunnel valley units. Some of them moderately connected, it appeared, others not so well connected. And this has been an area where there's been a lot of decline in water levels over the years from industrial and some municipal use. And there were always concerns that, you know, we were mining the groundwater in that area. And one of the reasons, if you look at the stratigraphy, now this is I'll go back here a second. We're going to look at this west, I want to point my finger, the West Fargo South. We're going to look at at a longitudinal section that Dave Ripley made for that West Fargo South. And you can see we've got these overlying lacustrine clays, thick sequence of glacial Lake Agassiz, and then glacial till, and then into our West Fargo South aquifer along this transverse or longitudinal section. And so one would think you shouldn't be getting much recharge into these kinds of segments with all this lacustrine clay and till overlying. And this is just a hydrograph of a well in the West Fargo North aquifer, where there's been some industrial use and municipal use. But you can see that it started to decline. We had some pretty hefty declines there. And then it started to flatten out as water use declined. But also, we were starting to convert from confined conditions to unconfined conditions. When you're in a confined condition, the storage that you're removing is what's called elastic storage. And so the amount of water that you remove from elastic storage per unit volume of an aquifer is really small compared to when you go to unconfined conditions. Now you're looking at drainable porosity, which is 3 orders of magnitude larger per unit volume than your elastic storage. So one would expect now you're starting to look level off if you're going to these unconfined conditions. But it's still, given the complexity of the stratigraphy, you're not quite sure. Are we getting some recharge at this point? Did we knock enough gradient, create enough gradient in that system to bring in some recharge? So Rip put together for each of these different segments, looking at the water chemistry. These are box whisker plots, and we're looking at total dissolved solids increasing here, and he's got these various segments, different tunnel valley areas. This area was really interesting here, the West Fargo South. We had very low total dissolved solids concentration, kind of a calcium, magnesium, sodium, major cation, and it suggested that, well, this has kind of a look of a recharge area. Are we getting some recharge into this West Fargo South area? So then Dave collected a bunch of samples, and the red here is the West Fargo South, again on our Oaks and our meteoric water line, and sure enough, it was very cold signature. It is not a modern meteoric water, probably in place during deposition during the Pleistocene. And if we look at all the samples that Dave collected in all of those segments of the West Fargo aquifer system, you can see, again, it's all in that cold signature, suggesting, again, that we're looking at non-modern meteoric water and not much recharge into that system. So to conclude then, continental glacial stratigraphic sequences can be complex. They're characterized by small-scale fluvial inhomogeneities, what we refer to as hydraulic short circuits that can facilitate groundwater recharge to buried glacial aquifers. And these hydraulic short circuits commonly are small-scale and not readily identified by test drilling or geophysical methods, particularly with the budgets we have for getting out there and doing test drilling. Analysis of stable isotopes, O18 and deuterium, are useful in identifying areas where these hydraulic short circuits may occur. And they're pretty cheap. Back in the day when we were doing it, I don't know what current, we used to send them to Waterloo and then a lab in California, but they were, I think, somewhere around $90, $80, $90 a piece. Do you remember, Royce, is that? But it was somewhere around there. So that's a pretty cheap versus going out and drilling a bunch of test holes. If you can look at a large area of an aquifer and be able to discern whether you're getting much in the way of recharge or not with a handful of isotope analysis, that's a pretty cheap method to answer a lot of questions on how you're going to manage that aquifer. So that's it. That's the end of the talk. If anybody has any questions or comments.
Did you and Steve us work quite a bit together since, because he went up and down, didn't he, with that aquifer, since you guys were side by side?
Well, yeah, actually, Steve didn't. Steve was more in the New Rockford, which is a kind of a tributary there to the Spiritwood. Uh, but he didn't do isotope work up there. John Patch did, and I could it would have made the talk much longer. I mean, there's a bunch of examples where the Warwick Aquifer overlies the Spiritwood Aquifer. That's a good area where John Patch did stable isotope and was able to show the leakance from the Warwick down to the Spiritwood in that area. And then there's also, and I don't know who collected those samples, the Wahpeton Buried Valley Aquifer in eastern North Dakota. That's the same kind of situation where you had a buried, the Wahpeton Buried Valley is a deeper buried system. And there were some short circuits in that they were able to determine using stable isotope. So yeah, just different investigators, because it's such a cheap, it's a very inexpensive way to answer a big question.
Wanted to find a way to work Steve's name in.
Yeah, well, he did some really good work up in the modeling. When we talk about these complex stratigraphic and geometric issues with regard to buried valley systems, because of what Milt allowed us to do, get out there and just drill where we thought we could see certain things occurring. We were able to really see barrier boundaries in these glacial aquifers, transverse barriers and longitudinal barriers, and how that affects your management considerations. And there's been a lot of work. The Canadians, we learned a lot from working with Garth Vanderkamp and others up in Canada. They did a lot of work on buried systems. And then Europe, they developed a project in the 90s there, early 2000s. It's called the Burval, where various countries contributed money to really do a lot of test drilling throughout Europe in the glaciated areas. And they've got it's a nightmare. There's all kind of advanced retreats, a huge complex situation of different buried systems that interact, and the plumbing is crazy. So yeah, we're very proud of what was accomplished here in North Dakota, the kind of work that the legislature and, gave us the money to move forward and do what we needed to do. We never had a no, can't go do this. So that was nice. Anything else? Royce, you're not going to nail me? He's given me grace here today. I used to work with Royce. Uh-huh.
Agricultural land, the crops really aren't starting yet. You're doing a big root system, so you aren't taking a lot of water out. So if you got a good snowpack, a system like oaks where you got Hecla sands, which is basically low water holding capacity soils, it doesn't take a lot to load the system up. So if you get good snowpack, you kind of fill the profile up, you push a little bit through, and then you get those. And then if you get a good late May rains into early June, then you can push on water on through. So you get that mixing of precip and snowmelt water across the landscape.
Yeah, and that's a big issue. It's just looking at moisture deficits prior to rainfall events. That's a key. And yeah, your crop, the maturity level of the crop. But that one time, it reminded me of being in Thailand during the monsoon. It was unbelievable. I'd never seen in North Dakota. It was just sheet fall. It woke me up, at the motel down there. We were supposed to get out and be working the next day. It was like the rest of the week. We were toast. There was just water everywhere down there. You couldn't get out with a rig or anything. And that's a sand plain, so I mean you can have some tremendous events that'll really provide recharge to that system. Anything else? Yep.
A little bit about, you said your diagram was, but these short circuits and like a glacial deposition perspective and what they are they, if they're very small scales, so they're just bits of glacial fluvial material between hills, or they're completely vertical.
Well, you can get, again, smaller, like considered like catastrophic, little local catastrophic flood events. You may get a small glacial lake that gets breached, and you cut a channel that can cut through a till, just locally, a little small feature, and then maybe fills up with sandy units or silty. Maybe the energy drops, but you still get some silty, sandy material in it. And those can be the short circuits through the till that can really provide. And I think the bigger ones are more these lacustrine features, like I used the example there. That's in Sargent County. That's that. I think it's referred to as Glacial Lake Sargent. There you have a fair amount of. It's another lake plain, and that's fairly pronounced. But it was fairly deep. You had a lot of silty, sandy, kind of leaky type deposits in that area. But you could miss it. You could maybe not drill if you're chasing down the spirit wood. Maybe you'd get one well in there that would say, well, is this just a little local, little small scale feature? It's not going to provide much. But yeah, the source, that's what we found with these hydraulic barriers that, in fact, in Sargent County there, if you go a little bit east of where I had that last nested piezometer area, there's a big head drop in the spirit wood of about 100 feet, just an abrupt water level, boom, just like this. Well, there's the only thing that can explain that is some kind of a barrier. And that's what Steve found up in Minot with the New Rockford Aquifer. Once that aquifer, the spirit wood, was developed, somewhere, glacial lake, whatever, small lake was breached. You had a catastrophic flood event, hit extreme down cutting, high energy, but short term. So you get very little coarse deposition at the bottom, and then as the catastrophic flood event dissipates suddenly, and now you wind up with just a very low energy clay that slowly fills up that cut valley, and there's your barrier. And we've actually drilled those out based on those head differentials. So yeah, glacial environments are, anything can happen.
Yeah. Tiny shale is thinning on the Dakota. Glacier's supposed to pressurize it to the point.
Shove block?
Yeah, well, it shot pressurized sand upwards.
Oh, the sand.
And and left these piles of sand that kind of look like canes, but they're different now, but right on the edge of the glacier. And then, so there would be, theoretically then connections vertically through all the unit sand that made that reverse then, and then allow meteoric waters down again. That's right on the South Dakota border. Very Coteau, but
Okay.
a lot going on down there.
Yeah, there is. There is. These glacial systems they were fun to work with. Yeah. Yeah.
As someone who doesn't have a background in glacial or sedimentology stuff, what about the till makes it hard for part of the infiltrate? Is it just the big, fairly sized boulders and cobbles that block slow?
No, it's basic. Well, as roughly speaking, your tills here in North Dakota, roughly a third sand, silt, and clay. Kind of a rough, I don't know, statement that you could make about hydraulic conductivity, the ability to move water through a substance. If you've got 8-10% clay in a mixture, in a deposit, you're basically looking at a very low hydraulic conductivity material, and that's your till. You know, there's a fair amount.
Just don't need a lot of clay for it to start happening.
Exactly. You get in your weathered zone now, where you get a lot of fractures and secondary porosity. There's where you're not looking at your primary porosity permeability as much as your secondary porosity. So your superficial till units, or even buried till, if you have a weathered zone, depending on how deep it is, you know, that secondary porosity permeability is your major, accounts for your flow system.
Gotcha.
It's much more dynamic. Yes.
A comment rather than a question. If if you've done work in a lot of different states and you're accustomed to the State Water Commission here in North Dakota, they don't even compare with the amount of data, the quality of data, the accessibility. And you're bringing up all these names, and Steve Pusk, and I'm thinking of Bill Shue and all the people that were in that office there that's not there now. What a great age. The stuff you guys did and the people that did it.
Well, they're still doing it.
Well, they may still do it. I'm not familiar with their data. I'm just saying that.
But Milt was a
Yeah.
wonderful leader. You know, if you really love a career, it's not a job, it's a career. Milt gave you the chance to pursue a career, and not just a job. And so, I mean, you'd go down at his office on Friday, 4:30 or whatever, 5 o'clock, and just chew the fat on. You got a problem? What's this? How are we doing that? Should we do this? That, you know, you were interested, and that's a wonderful environment. And to have a supervisor like that, that just, you could say, look, I want to go collect 018 deuterium samples. So how much does it cost? Okay. How many you want to do? Okay, go ahead. You know, and you did it, you know, and that's a wonderful environment to work in. So I was blessed. So I came back from Oman. You can make more money in Oman, you know, but it was much more worthwhile and satisfying to work at the Water Commission here in North Dakota. So,
Well, and being an outsider of the Water Commission and spending so much time with so many of those people, it was a golden age for me. The 90s and the early 2000s, and people there, and what went on, and dealing with the results of the work they did. Because that really, there's nothing like it in any other states. I mean, there's bits and pieces like it, but not the organization. I don't know if any other state has the county series. No, I mean, everything is just named.
well, and that was a cooperative with the Geologic Survey, the U.S. Geologic Survey, State Survey, the Water Commission, that got all that stuff done. You know, it's cooperation.
But I've also always thought that a really great idea would be to take the county series and modernize them. Take everything that's been done since there, and not necessarily discrete and just by county, but kind of organize stuff by county. So if you're in a certain area, then all the data that has to do with that area is right there.
Well, the data's there, you know, it's just that, you know, there's more of it.
Right.
You know, we've infilled, and the people are working there now. Every year they're adding new data in their project areas, you know, so.
With the structure of the county studies is just so valuable.
Mhm.
And trying to do anything. How does, and also you got, this guy did this study over here about an area that kind of overlaps, and you spend a lot of time fighting to figure out what, but in the county studies, it's like, here's the unified theory right here.
Well, as an example, when the, in the 80s there, when the EPA was looking at giving states primacy for underground injection of their UIC program, we went down to Denver to their region office and different Western states, and they were going to provide grant money to each state to do drilling and to collect some data for a database for evaluating underground injection sites. And we went down there with a handful of county studies and said, here's our data. And they just said, okay, well, we can still give you some money. We said, why not give it to Utah or some other where they don't have the money? Because, and then they said, well, how can you say? So we handed them the county studies. They said, oh, got it. That's fine. You guys can have primacy, have at it, and so, I mean, that's, and it's due to your legislature, they're the ones that funded that in the 50s, the 1950s, 55, I think was the first, was that Roger Burley or with Randage or Stutzman? Kidder. Okay. And 55, I think we ended those studies in the 90s. And even through dry spells where money was hard to come by, they kept going with those county studies. They were very prescient with regard to water resource in this state, which is great.
Yeah, things were different in those days.
Yeah. So, any other questions?
I was just following up with the comment. I went to Bell 90s. I said, Bell, start all over and update these. They said, oh God. Said so many projects he had to set aside to finish those things. So he was very glad to be done with that series.
Yeah. So that's the problem, trying to balance regulatory work, and that's your primary function. But then you also have to collect data to, perform that regulatory function. So you can't be just chasing data all the time either. They're knocking at your door to make decisions. So. All righty.
Yeah, there weren't any questions online, so.